Hello. Oh, hi. I'm Dan Grabois. This is SoundWaves. This is our 14th year of SoundWaves and going strong. And all year this year, we're looking at development, how things change, grow, develop. Our final event in the spring, our fourth one, will be on April 11th, and that is over at the Meadwitter School of Music in the Hamill Music Center in the big hall, Meadwitter Foundation Hall. So please come. Please bring 10 to 30 friends because it seats about 650 people. And we'd love to fill it. We don't have that program planned yet. That is still in development. I'll be speaking to you later tonight, so we will begin with our first presenter.
Good evening. I'm Jennifer Van Oss from the Department of Animal and Dairy Sciences, and I do research and extension outreach on dairy cattle welfare. So today I'll be talking about giving cows a voice through science. Wrong way. So who here has a vehicle with one of these? Okay, so notice what it says on the bottom. Wisconsin is America's dairy land. Our state is second in the nation for the number of dairy cows as well as fluid milk production, but we're number one in cheese production and the number of dairy farms. And we couldn't do this without our dairy cows. We have over 1.2 million dairy cows in the state, plus calves, heifers, beef cattle, etc. So this is a real Wisconsin dairy cow. We'll call her Clover. So when we think about Clover and we take a look at her, how can we tell if she has a good life, if she's experiencing good welfare? You'll notice that I cut this picture out from the background. So when you're looking at this picture and you're filling in the blanks, what kind of environment do you instinctively imagine that she lives in? I think many people might imagine that Clover lives in a pasture full of clover. And there are many farming systems worldwide where this is the predominant type of environment that cows are raised in. And actually in Wisconsin, we do have the highest percentage of grazing farms in the country, but we're talking single-digit percents. This is where I actually captured the image of Clover. So we call this a naturally ventilated, sand-bedded freestall barn. And this is a very common housing type in Wisconsin and many regions of the US as well as worldwide. So depending on your familiarity with dairy farming, you may have a range of different reactions to this kind of environment, depending on if you've seen this before or not. So how can we determine whether this type of environment results in cows like Clover experiencing good welfare or a good life? So part of my job as an animal welfare researcher is to try to ask these questions since we can't ask Clover directly and have her respond in our human language. My daughter is a preschooler, and she has this book called How to Speak Moo. So we're trying to get her started early to be able to communicate with cows like Clover and be able to have this dialogue and develop this understanding. But for those of us who didn't start early with this type of reference guide, we have tools in our arsenal to ask clever questions through experiments to try to infer what cows like Clover think constitutes a good life. So I'll introduce to you one of the common frameworks that we use in animal welfare science. So this isn't the only one, but it's one that I'm a fan of because Dr. David Fraser, who developed this concept, is my academic grandfather. So this framework actually was originally intended to capture the range of different values that people hold when they're thinking about animals under human care, because different people have different priorities. But we can also use it as a way to frame research questions and generate testable hypotheses. So when we're thinking about welfare, I think intuitively we might think we could care about an animal's biological functioning. So this is what we think of when we're talking about classical physical fitness or evolutionary fitness. So things like, is the animal healthy? Is she experiencing injury? Is she productive in the case of dairy cows, or is she reproductive? But biological functioning in and of itself is not sufficient for an animal to have good welfare. And that's because biological fitness is also an attribute of non-sentient organisms like plants. There are scientists who study, say, plant pathology and care about the biological functioning of plants, but we're not concerned about plant welfare. So a key point to make is that when we're talking about cows, like Clover, we need to recognize that they are sentient and they are capable of experiencing emotions. And that doesn't mean that they're directly akin or analogous to human emotions, but we need to recognize that scientific studies have shown that cows can experience positive affective states or emotions and negative ones. We want to minimize those negatives and try to maximize the opportunities for the positives. So this really is the core of animal welfare. If we're taking care of sentient species, we need to understand if they're experiencing positive, subjective internal states or negative ones. So of course, one of the things that can affect how an animal feels subjectively is her physical state. But another important consideration is her ability to live a relatively natural life. And this is what we call it within my field, but I think this phrasing can sometimes be confusing. Because when people hear natural living, and we're thinking about it in terms of people's values, we might picture Clover standing in a pasture because that appears more natural. But when we're thinking about animal welfare and studying that from a scientific perspective, we don't necessarily mean that an animal must be in an outdoor environment to experience natural living. What we're actually talking about is their ability to express important adaptations, especially behavioral adaptations. So we have to understand that species' evolutionary history, and we also have to understand where an animal is in her development. So what life stage is she at? And if they aren't able to perform important behavioral adaptations, they can then experience negative affective states or negative emotions. So some of the tools that we use to investigate what animals need to have a good quality of life are techniques called preference testing, which is exactly what it sounds like. So we can design tests to find out what animals prefer. And there's another technique that we commonly use called motivation testing, where we can design experiments to allow animals to tell us what's important to them. So in order to understand the evolutionary history of cattle, we can look at clues in their current behavior to infer what their adaptations are. So the wild ancestor of domestic cattle is called the aurochs, which is now extinct. What I'm showing here is an artist's rendering of a scene in temperate Europe over 100,000 years ago. And so what you can see is this light forest landscape with the aurochs lying down under the cover of trees. Humans began interacting with the aurochs many thousands of years ago. So there are cave paintings, we're not sure exactly how old they are, at least 11,000 years old, showing the aurochs. And it's thought that they were domesticated around 11,000 years ago in Europe, and that there may have been 3 separate domestication events in Europe, Africa, and in Asia. So humans have been developing our relationships with cattle for a long time, not just in terms of domestication, but also in terms of hunting. And I mention that because we need to acknowledge that when we're talking about welfare, we're taking into account evolutionary history and this natural history in terms of the human-animal relationship, and cattle are a prey species, which means they perceive the world differently than humans do. And that's why it's important that we do these studies, so we don't just assume that what would lead to a good life for us would lead to a good life for cattle. That's why we need to do these studies. So what I want to show here is this juxtaposition side by side, because one of the tenets when we're talking about applied animal behavior is the understanding that when you domesticate animals or keep them in captivity, it doesn't change their fundamental nature. So it doesn't change what we call their behavioral repertoire or their instincts. It may just change the degree to which different behaviors are expressed. So on the right side, you're seeing part of this artist rendering of the aurochs over 100,000 years ago. And on the left side is a photograph that I took in Australia last year, where you can see domesticated Holstein dairy cows under the cover of trees. So shade seeking is part of the natural behavioral repertoire of cattle. So when we think about Clover and the environment she lives in, we can't make judgments just based on which environment we think looks more natural or more pleasant, because even this grass pasture is not actually the context in which the aurochs evolved. And so when we're thinking about what kinds of environments or what kinds of management practices or interactions humans have with cows and how that affects their welfare, we need to not just look at these environments through human eyes, but understand what it means through a cow's eyes. So interestingly, when I took that video, it was a screenshot or a video of Clover, she actually was in this barn, this white barn in the background there, which is the dry cow barn at our UW-Madison research facility in Arlington. And seasonally, those cows actually have free choice in and out access. So when I found Clover, she was inside the barn, but some of her peers were here outside in the adjoining pasture. And I really like this type of environment where cows have choices. We call this agency because it allows for individual expression of their priorities. And research studies have shown that if you ask a cow, do you prefer to be inside the barn or on the pasture, the answer actually isn't clear-cut. It's context dependent. So cows are motivated to have access to pasture sometimes, but remember that they evolved to seek shade. They become overheated much more easily compared to humans, especially with domesticated cattle who now produce a great deal of milk, which takes a lot of work for their bodies. So having these choices allows them to seek shade inside or to come outside to perform other behaviors. When cows are housed inside, there are ways that we can do research to develop ways to enhance welfare in these indoor confined environments. So one example I want to highlight is the use of brushes. So this is what we call an environmental enrichment. And brushes are something that studies have shown that cows prefer, and they're highly motivated to gain access to. It's something that they enjoy and is important to them. So when we're thinking about this three-pronged approach to looking at welfare, brushes enhance cows' biological and functioning. It improves their hygiene and cleanliness, but it also allows them to express this important natural behavior of grooming, and it's something that they are highly motivated for, so we know it's something that improves their emotional state. And it's not just adult cows who enjoy using brushes, so when we're thinking about the development over the course of the lifetime of cattle, studies have also found that young calves and heifers willingly use them as well. So in my lab, we've looked at lower cost solutions compared to those fancy rotating brushes by providing heifers with these low cost simple brushes, which they use immediately the first time they see them, even if they've never encountered a brush before. So this is an example where when we have these simple brushes, not only is it lower cost for farmers to implement easily, but also we observe that at these earlier life stages, the way they use them is different. So calves and heifers not only groom themselves with the brushes, they also explore them with their mouths. And this is something that makes sense in the course of their development and in the course of their evolution, because young animals are still drinking milk. So suckling and performing these oral behaviors is something very relevant to them. So I do work directly with dairy farmers in my extension outreach capacity to try to come up with these practical solutions to improve animal welfare. But I also work with the broader industry at a national level through advising to provide evidence-based solutions so that we can establish nationwide standards and set expectations for all farms. So I want to make you aware of a national program that virtually all dairy farms in the US participate in, and it's called FARM, or Farmers Assuring Responsible Management. And this program is, it's something where we have a committee, and I'm one of 4 science advisors, but there's also dairy farmers and veterinarians and representatives from milk processors and cooperatives. And we come together to try to come up with these standards that are informed by scientific research, but also balance these practical realities that dairy farmers face. And one of the priorities that this program has established is that people on farms are expected to interact with cows appropriately, because cows see the world and react to humans differently than humans see the world. It's something that requires training. So one of the things that we develop in my lab is resources for continuing education so that people who work on farms can understand how to interact with cows appropriately by understanding their natural behavior. And so what you can see in this video is that when you understand the natural behavior of cattle, it's kind of like a dance where you can get the cow to move to where you want her to go using your body position or body language. So we're developing these resources so that people on farms can develop good habits. I want to quickly highlight to you one other continuing education resource that we've developed, and this is something that you can try at home.
Cows. Practice moving cows around a dairy farm by using your body language. It's time for milking, so the cows need to be moved from the pasture and the barn and loaded into the milking parlor. Learn about cow behavior and practice cow handling skills to stay safe and keep the cows calm. Pass all 8 levels of the game to earn a certificate of completion. Moving cows is approved by the Farm Animal Care Program for continuing education on stockmanship. Play it in English y en español. This educational game was designed by the University of Wisconsin-Madison, with help from people who work on real dairy farms in Wisconsin. The game is completely free, with no ads. Download Moving Cows for Apple and Android mobile devices.
So I hope you'll check it out, because if you do, you'll be well on your way to developing your ability to speak moo. So in closing, what I hope that you'll take away is that by doing scientific research, we can develop evidence-based animal care practices so that we can improve the lives of cows. And in closing, I do want to also thank my many funding sources. I also rely on federal funding from the U.S. Department of Agriculture, to which I'm very grateful, and I hope that that will continue in the future. Thank you.
You set me up really well. In fact, I will start with federal funding. We would know nothing. My research would not happen. So please, please. Anyway, I am really happy to be here, and I want to start by just getting you to think about language for a moment. So everyone in this room is a native speaker of at least one language. Some of you are native speakers of more than one language. And because we use language constantly and in like every moment of our day, we don't think about it very much. And yet we're doing extraordinary things. As you listen to me right now, I am speaking at a rate of about a syllable for every 150 milliseconds. So I'm talking really fast, but you understand me, right? I'm using sounds that are familiar to you because you speak English. I'm using words whose meanings you can access because you speak English. You are able to figure out where my words begin and end, even though I don't talk like this, something I'll return to. And you know a lot about the structure of your language. You know that the sentence, the dog bit the man, means something fundamentally different than the man bit the dog. And so in my research, what I want to understand is how this knowledge develops and how we can find out. And this is the part that's going to relate to Jennifer's talk, because we also use preference. Because we can't ask babies to answer questions, raise their hand, press buttons. And so we have to get at their knowledge in subtler ways. I will note that some of what I'll talk about today is my own work, and some is work by brilliant people in my field. If I give a one-sentence blurb about something, and you're like, hey, that's cool, reach out to me and I can give you the actual reference. I didn't put the references in the slides. Okay, so people often think, colloquially, that language learning starts when the first word starts. So you're a parent, and you are desperately waiting for that first word. That is like your semaphore of language. But that's wrong, actually. I mean, it's cool, don't get me wrong. Like, it's really cool to get that first word, but it turns out that what babies know is vastly underestimated by what they can say. And indeed, during the course of the first postnatal year, and even before babies are born, they are learning about language. Language learning occurs as early as we can measure it. And so what I want to do in the first part of my presentation is just give you like a brief developmental timeline of some of the amazing stuff that is going on under the hood during that first year of postnatal life. So newborns, right? They are squishy. They can't pick their head up. They can't do anything. But they're already learning language. So the first note I have up here is that newborns prefer their caregiver's language. In fact, fetuses learn about the sound of the pregnant parent's language. They learn the rhythm of the pregnant parent's language while they are still fetuses. And you can demonstrate that when you test them after birth. So they have some pretty amazing stuff already going on, but at the same time, this point here, they are still sort of prepared to be citizens of the world. They can be exposed to any language. It doesn't matter where they're born, who their parents are. They can still perceive all the sounds of all the languages of the world when they are born. So they are ready. They are set. Very quickly, they start to learn specific things about their native language. The first word that babies seem to recognize happens around 4 months of age. I'm going to ask you to guess what it is in a moment. By saying recognize, I don't mean babies know the meaning of this word, but I'll show you how we know this in a moment once you know what it is that the first word is, just that they recognize the sound of this word. Anyone want to have a guess about the first word that babies tend to recognize? Their name? Yes, their name. Very good. Because that's what they hear the most. Oh, look at little ba-ba-ba, ba-ba-ba. They hear their name a lot. Now, how do we know this? This is where I want to get into the methods. How do we know that babies recognize their name? We use preference. So the way you could do this, here's Dan, I'm Jenny. Let's say you have a baby named Jenny. That's my name. You would have the parent come into the lab, their baby's sitting on their lap, parents wearing headphones so they can't hear what the baby's hearing, and there are audio speakers on both sides of the baby. And one side is going to start to repeat, Jenny, Jenny, Jenny. Baby will turn their head to look at the Jenny, and it keeps going as long as the baby keeps looking, turns off when the baby looks away. Next trial, Dan, 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 keeps going as long as the baby keeps looking. And what you would find is that a baby named Jenny will look longer to Jenny, and a baby named Dan will look longer to Dan at 4 months of age. Now again, it doesn't mean that I know that me, baby Jenny, knows that I am Jenny, just that those sounds are familiar. 4-month-olds, they can't crawl, they can't sit, but they're already learning the sounds of their language. There is something really basic and just intuitive about this process. Things get fancier as babies get bigger. So by 6 months of age, babies perceive the vowel structure of their native language differently than the vowels of other languages. So they're getting good at vowels. And they're also starting to do this thing that I alluded to before about figuring out where words begin and end. Come back to that. And they also start to now understand words. And we know that because if you show a 6-month-old a display like this, and you say, the computer says to the baby, where's the apple? Can you find it? We measure the baby's eye gaze, and the baby, oops, that's not what I meant to do, and the baby will fixate that apple after hearing the word more likely than chance, which is evidence of early word knowledge. So we can get inside their heads at this very early point. And then they just get fancier and fancier. By the time they're 8 to 12 months of age, they can no longer perceive consonant pairs that are not in their native language. That's a lot of learning that's going on, completely clueless by the parents. It's not like parents are like, I need you to learn the distinction between ba and pa today. This is not being taught. It's just in their world, and they're soaking it up. So All of this fancy stuff is happening before that 12-month-old miraculous moment of the first spoken word. In parenthesis, everything I just said is true in bilingual infants too, despite having to learn twice as much in half as much time, because if you're awake for 10 hours a day and you have 2 languages, you only get 5 hours a day of language. They're not delayed. So really important point here, multiple languages, only a good thing, okay? So in my lab, what we want to understand is how did babies do this? How do they figure out how their language works? And what happens when things aren't going quite right, as they often do not? And we have been particularly focused on a particular kind of learning that's going to sound really counterintuitive to you until I explain it. And that is the idea that part of how babies learn about their native language is by tracking the statistical properties of the language. Part of what babies are doing is math. Now, that sounds counterintuitive because we don't think about babies as taking like our graduate stats courses and doing all this fancy stats that some of you probably know. What I mean instead is something much simpler, that babies are sensitive to probability. They are sensitive to what predicts what goes together. It turns out that I'm not going to go into this in detail, but if you look at pretty much any structure in natural languages, it has statistical ramifications on the surface. There are patterns that a suitably equipped learner could pick up on that could help that learner figure out how the language works. And to make this point, I want to give you a specific example that we've studied a lot, that we think is actually driven largely by this process of tracking statistics, even in very little people. And that is this problem of figuring out where words begin and end, in the immortal words of Gary Larson and his most famous cartoon. So here's the problem. There are no pauses between our words. They don't exist. So when you look at text on a page, there are those little white spaces between words. When you think you hear little white spaces in our speech, that is an illusion. It doesn't exist. And you can prove that to yourself very quickly by listening to someone who speaks a language that you don't know, okay? And so the question is, how might babies figure out where the boundaries are between words? So take this sequence in English. Is that 1 4-syllable word, 1 4-syllable word, 4 1-syllable words, a couple of 2-syllable words? How would you know? There's no pauses. How would you figure this out? Well, there's statistics that can tell you. So in English, if you hear the syllable pr, sometimes it's followed by t, sometimes it's followed by tend, pretend, predict, prevaricate, predilection, that's about it. The point is that if you hear pr in English and you're a baby, it's a pretty good bet that the next syllable is going to be t. That's like a reasonable bet if you were laying money on it. Whereas when you go from t to bay, bets are off. Pretty shoes, pretty dress, pretty cake, pretty mama. You cannot predict what's going to happen after t in English. And so the intuition here is that sequences that are part of the same word clump together with high probability, sequences across a word boundary clump together with low probability. And in point of fact, I did do the math here. I'm not just asserting this. Well, we need some audience participation. It's late. I'm going to have you guess. If you hear you're a baby under the age of 1, if 100% is every time you hear pr, you hear t next, versus 0, every time you hear pr, you never hear t next. Anyone want to take a guess? What percent of the time after pr would you hear t if you're a baby learning English?
96.
96? That was very assertive. It's close. But here's the interesting one. T to bay, what's the probability? 1. Any other guesses? 25? All right, we have a big range. It's vanishingly small. It's vanishingly small because so many things can happen after t. So if you're a learner that could pick up on these probabilities, you can solve the word segmentation problem. You can figure out where words begin and end. And so what we did long, long ago was to test this in babies. So how would you test this in babies? What we did was we made up a language and we played it to babies in the lab. Would you mind playing that sound file for me? So basically what we did, this is actually a better depiction of it, was we played this for babies, but it has structure. I'm actually the only native speaker of this language, but it has words in it. These are the words. They're arrayed in random order. And the idea here is that some sequences are highly probable. So in this particular language, every time you hear toe, it's followed by ki. Every time you hear ki, it's followed by bu. Very strong clue to that sort of cohesion of that unit. But then bu can be followed by lots of things. Bu can be followed by gi or go or other things. And so we can contrast that with sequences that go across a word boundary, sort of like T-bay in that pretty baby example. And we can ask, if we have babies listen to this sequence for a couple of minutes, will they then be able to tell the difference between these words versus sequences that aren't words? And so that's what we did in this study. If you're interested, I'm just going to sketch this, but if you think this is interesting, Netflix did a documentary called Babies. We are episode 5, so check us out. I got the best street cred for my kids ever. When I said Netflix was coming to film, they thought, and my daughter's actually in it. So here's how we would do this study. We're still going to use preference. How am I doing on time? 5. Perfect. OK. So the way this study would work, I'm going to show you a video in a moment. For the first 2 minutes, the baby's going to sit on a caregiver's lap, and the baby's going to hear this stream of speech. Topi boo go la poo pa boo dee pa boo poo toop ti boo go la boo too ti boo for 2 minutes. Gets pretty boring after a while, especially if you start to pick up on that structure. Then after 2 minutes, the room goes silent. We have an experimenter outside who's running the study, and they hit a button that starts a light blinking on one side of the room, and it's going to repeat either a word or a part word from this language. So the baby's going to hear go la boo, go la boo, go la boo, as long as the baby keeps looking. When the baby looks away and stays away, then the experimenter hits a button, the sound turns off, the light turns off. We blink a light in the middle to get the baby's attention again, like you were talking about, like we're trying to take advantage of things babies like. Blinking lights are one of them. And then we'll start the next trial. So let me show you a video about how this works, if you don't mind playing the video for me. I'll narrate. Okay, center light's on. Side light. Baby looks away. Center light's on. Side light. He looks away, but he comes back within 2 seconds, so we keep going. And he is done. And so the idea here is that the baby is the boss. The baby controls how long we play each test item, and that allows us to then draw conclusions from a lot of babies, about whether infants are able to make these sorts of discriminations. And indeed, oh, that was animated. Babies are really good at this. So in the subsequent couple of decades since this work was published, there have been hundreds, if not thousands, of papers demonstrating sensitivity to these sorts of statistics in adults, children, newborns, even newborn infants can track these statistics. We've studied this in many other aspects of language. We've looked at real languages, not just these artificial languages. Can you play the next sound file?
Ho coricato all'ombra del melo verde. Per ascoltare la fuga, quasi cadi sul melo e inciampi sulla birra o sull'erba.
So that was Italian, and infants track the statistics in that as well. We can demonstrate that in the lab. And then, of course, we've looked at lots of other domains, and I apologize to the musicians in here. This next set of stimuli is words that are made out of sine wave tones. And so now instead of a word being go, la, boo, a word is A, C sharp, F, or something like that. So can you play the last video? And infants can track those statistics. And again, for the musicians, you might find it interesting to know that one thing we found is that babies track sequences of absolute pitches. So babies track A, C sharp, F, whereas adult non-musicians track relative pitches. So they track things like ascending perfect fourth followed by a descending minor third. Very interesting, but that's not what this talk is about. So one thing you might perhaps be thinking is, this sounds a lot like things we see a lot in the media right now. And indeed, what babies are doing is not deeply distant in many ways. Of course, large language models have access to massive amounts of written text, and babies don't. But the basic idea, the idea of tracking what predicts what and learning from prediction errors, is exactly the same at its most basic level as kind of what, moving past the proprietary aspects of these software programs. The basic idea is the same. Okay, so I want to wrap up by saying that one of the important things that we have done, in addition to studying basic aspects of how babies learn, is applying this work to trying to understand trajectories that are not following typical patterns and trying to figure out ways in which learning for children with different types of developmental disabilities might unfold in different ways with implications for interventions. So my lab is at the Weissman Center, which is a research center for developmental disabilities. And so that leads to a natural kind of melding. So I want to just end by thanking our funders, and most importantly, the many, many, many thousands of infants who've participated in our research over the past 27 years here at UW-Madison. So thank you very much.
Hi, so I'm Mike from the Computer Sciences Department. When Dan invited me to come talk to SoundWaves, I thought a lot about how do I explain what I do, because I'm dealing with sort of the inner parts of computers, and some people, when I talk to them, can be a little intimidated about how the inside of computers work. And so I thought about sort of, what is a good analogy that I can use to explain, and so I went through my favorite children's books and thought about who has great pictures of things that I could use. So this is a Richard Scarry book of a power plant, and I thought, how is a power plant like an operating system? You've got raw materials coming in from the coal at the bottom, it's sort of creating things that then is used to power the applications down in the bottom. We've got your kitchen going. And this didn't quite work for me. So I next turned to artificial intelligence, and I said, can you draw me an analogy for an operating system? And it came up with a factory with trucks moving in and out. And again, it really wasn't what I was looking for. So I went back to Richard Scarry, and I found this picture of a grocery store. And I felt, this is something I could work with. That there's a lot of ways, as I'll show you, that sort of what an operating system does is a lot like our food production and delivery system. And both the grocery side of it and the sort of cooking aspect has a lot to do with what operating systems have to do. So how is that? Well, let me first sort of take you back to the dawn of computers and explain what is the problem that an operating system solves. So this is a picture of the first commercial computer, the UNIVAC 1 from 1951. It's sort of most famous for predicting the election back then. This was a great computer. It was a giant computer, and it was incredibly stupid and dumb and could barely do anything, but it was still a miracle. So the problem with this computer was twofold. One, it could only do one thing at a time. So if you wanted to do something with it, you would sort of bring your program in, the operators would load it, they'd run your program, it would take a couple hours, they'd produce something, they'd then load somebody else's program in, it would run for a couple hours, produce a result. So it was sort of very cumbersome and only did one thing at a time. The other problem was that it was very, very complicated to work with. You basically had to give it incredibly detailed instructions about take this piece of data and add it here and put the result here. Which of these tape drives that you see on the right do you read things from? Which of the switches on the console panel do you flip to enter the numbers you want? It was incredibly tedious, and this is sort of why software became important, because people realized that the software for computers was actually much harder than building the hardware, which is why we have so many programmers today. So how is this like food systems? Well, sorry, let me back up a little bit. So operating systems were invented to sort of address this problem. The job of an operating system like Linux or Windows or iOS or Mac OS is to sort of tame this unruly hardware and make it sort of accessible to programs and to users in sort of a much more convenient, simple way, and really handle all of the complexity that goes on inside. So the analogy to food comes here, which is to think about what is our food system like today. If you go back a couple hundred years, or you go to other places in the world and you go into a store, you don't find frozen pizza. What you find is raw ingredients, right? You find grain, you find flour, you find vegetables, maybe some oil, milk. But if you want something, you have to make it yourself. My cousin, for example, lived in Peru for a while, and she said, you couldn't buy pasta. You could buy flour and make pasta, but you couldn't buy pasta or spaghetti sauce. You could buy flour and tomatoes instead, and the rest was up to you. And this is very much like what an early operating system was. if you wanted food, you had to basically do all the work every single time of taking those ingredients and combining them to make the food that you wanted. You didn't have the ability to go buy a frozen pizza at Woodman's. So this is sort of what operating systems do, is they sort of combine these raw ingredients that the hardware provides, the ability to add numbers, to move data around, and they give you much more convenient things to work with, so you don't have to sort of start with raw ingredients. Now, I want to point out, it doesn't mean that if you're a chef, you can't make your own pizza anymore. If you really care about the low-level details and the bits and the wires and everything, you know, have at it. But the fact of it is, most of us don't care. Most of us would rather have, you know, moving cows on our phone than worry about this level of thing. So here's an example of how this manifests itself. So this is a very early storage device. This was developed at IBM in the early 1950s, and it's called drum storage. It came out before hard drives, and basically it's a spinning barrel inside a cage, and the cage has a bunch of wires on it, and the drum is covered with magnets, and as the drum spins, the wires can detect the magnets going by, and each magnet stores one piece of your data. So if you were using this, you would sort of have to think about, where on this drum is my data? How long does it spin for before my data is underneath one of these wires? Then I have to turn the wire on and read the data and get it out again. So it's a big, complicated process that you wouldn't really want to have to deal with. Things are a little better. This is a modern hard drive. We now have a disk instead of a drum. It turns out it's more compact, but we still have this little arm that moves in and out, and somebody has to worry about, as this disk spins around, where is the arm, so that when your data is there, the arm is in the right place to read the data off the disk and get it into your program. And again, you don't want to deal with that. The person writing your moving cow program doesn't want to deal with this. It's the operating system's job to deal with it. So how does it do that? Well, IBM knew they had a problem. So in the mid-50s, they said, we're going to have a new invention. We're going to call it the file. Some of you may have heard of files. It turns out that modern undergraduate students don't know what files are, which tells you how much things have changed. I heard this from somebody in one of my classes. But the idea of a file is that you now have a collection of data that's all related, that has a name, and you can just say, you know, give me my final exam, and the operating system will find your final exam. So this was good. It was good when only one program ran, and when one person used a computer. But at MIT in the early 60s, they decided we wanted more than one person using a computer, and they now had to worry about two people naming their files with the same thing. How do you keep those files straight? How do you coordinate with all the other people in your lab to have differently named files? So they invented the folder. So we may think of this as like, you know, air and sliced bread and things like this, but somebody invented it to solve this very particular problem. And this idea that we're going to take this very low-level device and we're going to give it to you in terms of a higher-level object, or what we call an abstraction of files and folders, really is what an operating system does to make your computers usable. The other thing that operating systems do is they hide a lot of the details. So going back to our cooking analogy, if I want to do some baking, I can go to a store and I can buy flour. I don't have to worry about where the grain was grown, how it was milled, how it was cultivated, who the farmer was, what kind of cows brought it to market. I just know that I can go and buy flour, and wherever I buy flour, I can use a recipe and the recipe will work. And the same thing is true with operating systems. I can store my files on a zip drive, a jump drive, a thumb drive, a floppy drive, a hard drive, an SSD, a CD-ROM, lots of different ways of storing files. But the fact is that my programs don't have to know how to do that. I don't know how to do it. The operating system handles all of that. So it can take any of these devices you see here, plug them into your computer, a little icon pops up on your screen, you can get your files. You don't have to worry about any of the details because the operating system has hidden all of this behind this magic of files and folders. So to some extent, this is the crux of what an operating system does for it. It takes this collection of chips and pieces of hardware that might come from lots of different companies, and in fact, every phone might have a different collection, or every computer might pick a different set of chips, and it magically takes this collection and turns it into a wonderful device where you can download an app from an app store and it just runs. You don't have to think about what's inside your computer, and the App Store developer doesn't have to think about it either. So far, I've talked about one of the great things operating systems do, which is abstraction. I now want to talk about two more things. And the next one is what we call virtualization. So the fundamental problem that we want to solve is, how do we do more than one thing at a time on a computer? So this is a picture of my older brother, Andrew, back in 1981. This is the first computer my family had. And on this computer, you could only do one thing at a time. So if you wanted to switch between programs, you would save your files, you would then exit the program, load a new program, load your files, start working, and when you were done, you would switch and go back, and it would take a couple of minutes to go between each things. The reason it could only do one thing at a time is because the brain of this computer, which is like the size of a pea in reality, it really was a pea brain, could only do one thing at a time. And there's only one of these brains in the computer, and so that brain was fully occupied running this one program. And so the question is, how do we do more than one thing at a time if we only have one brain in our computer and it can only do one thing at a time? Well, think about what happens if you want to make a fancy meal and you have a one-burner stove, right? The way you handle things is you sort of switch back and forth your pots. You know, you cook something for a little while, you might take it off, you might put your sauce on, cook your sauce, take it off, boil the water for pasta. Once the pasta's cooked, you can reheat the sauce, mix things together, right? You can sort of move things between the burner and the counter so that, you know, everything kind of cooks enough at the right time when it needs to cook, and at the end, all of your food is hot and ready to go. This is exactly what operating systems do. They say, we're going to take our processor here, and we're going to start running just one program, say your web browser. When you want to run something else, like you want to write your mammoth newsletter, what we're going to do is we're going to stop running the first program very quickly, but leave it in memory so we can get to it right away, and start running the other program. And then we're going to stop running that, and we're going to go back. And in fact, we're going to do this 1,000 times a second. It's so fast that you can't see that it's happening. And in fact, the programs can't see that it's happening. The programs think that they are the only ones using the computer because time just goes by so naturally for them that they have the illusion they're running all the time. And so this is one of the ways that the operating system takes this processor that can only do one thing at a time and then virtualizes it so that we can run 2 programs or 3 programs or 10 programs at the same time, and they all think they're running alone. So the other major thing the operating system has to deal with is memory. So memory is the part of your computer that stores the things you're currently working on that you want to get to very quickly. You can get the data in memory in maybe 100 nanoseconds. And so that's where you want to keep things because it's very fast to access. The problem is that it's kind of expensive. So this is a picture of magnetic core memory. This was kind of the first popular memory. It's made out of little donuts of magnets with wires running through them. So every one of these donuts is 1 bit. This whole thing is maybe 2 kilobytes or something like that, maybe 1 kilobyte. And the question is, what if you want to bring up a big spreadsheet, maybe a spreadsheet of all the stars in the galaxy, on your computer and you don't have enough memory? What do you do here? So one option would be that the programmers at Microsoft could say, we're pretty smart. We are going to sort of very carefully move your data between your storage device and memory and move it back and forth and try to predict exactly what you will need and have it in memory when you need it. But that's really hard. So the question is, really the same question that happens is when you go shopping at Woodman's and you bring home 50 pounds of groceries, how do you fit them into your freezer? Right? So you've got a lot of groceries, you go to a small freezer. How do you take more groceries than you can fit in your freezer? And the answer in my family is we get a chest freezer and we put it in the basement. Right? So we don't try to keep everything in the kitchen all the time. We keep the things we're using in the kitchen, and the things that we're going to use later, we keep in the basement. And then somebody comes along and moves things around between the kitchen and the basement. In this case, it's my wife who's sitting right here. And so she will sort of think, what are the things that we are going to need, and bring it upstairs? What are the things we're not using? Take it to the basement. And then it feels like everything that I need is always in the freezer upstairs because it has been put there, and only occasionally have to go to the basement to get new things. So this is, in fact, exactly what operating systems do. So this is a picture showing on the right a computer developed in England called the Ferranti Atlas. And it had this idea of what we call virtual memory. And what they did was they combined this drum storage device and this magnetic core memory. And they said, we're going to run your program, and we are going to pretend everything is in memory all the time. And if something happens to not be in memory, we're going to pause your program, go out to that drum, get the data, bring it in, restart the program, and you won't even know the difference because when you start up again, you will not have noticed that time has elapsed, and your data will magically be there. And at the same time, we'll take some of the data that you're not using right away, and we're going to put it on the drum to make space for what we just brought in. So the operating serves the purpose of my wife of moving data between memory and drum storage. So this actually works pretty well. It's pretty widely used. The challenge that comes up now is how do you decide what you actually keep in your kitchen freezer versus what you keep in the basement? So this is a hard problem. It stumped a lot of people until the late 60s. A guy at IBM named Belody studied this and actually came up with the sort of mathematically perfect way to do this, what we call the optimal algorithm. And what he realized is the best thing you can possibly do is to get rid of the thing from your kitchen freezer that you're not going to use for the longest time in the future. So if it's March and you have a turkey in your freezer, that is what should go to the basement because you won't use it until Thanksgiving. Now, this is a great policy. The problem is you might notice that word won't need for the longest, which also means future, that it requires predicting the future. And much as we have machine learning, and I'll touch on that a little bit later, operating systems and computers can't really predict the future. So what the operating system does really is we think that the past predicts the future, so we will look at what happened in the past, and hopefully the same things will happen in the future. So operating systems really do two things. One, they will look at what are the things you're using the least frequently. You know, the things you only get out occasionally, maybe those things should go to the basement freezer. The other thing they do is we'll look at what are the things that you haven't used for the longest period of time. You know, the hot dogs that are sitting there getting freezer burned because you're not eating hot dogs anymore, maybe those should go to the basement, or some combination of the two. And so this is exactly how your computer manages things. It looks at what is the data sitting in your memory you haven't used recently or frequently, and that data gets moved off to your hard disk to make space for more important data so your programs run very quickly. Now, the final thing I want to talk to is, I mentioned before that you can run two programs at once, but there's a challenge of deciding which one to run at any given microsecond because they both might want to run. So suppose you're running a simulation of the air over Sydney, Australia. This is a long-running scientific computation. It might run for hours or days. At the same time, you're working on your woolly mammoth newsletter. And the operating system had to decide which of these do I run. The simulation might be very important. It's the future of your research, but that newsletter is pretty compelling too. What do we do? Well, the fundamental problem they're trying to solve here is the same thing a grocery store does when you're checking out. There's multiple people who want to check out. There's one cashier checking out. That cashier has to decide who do we serve next. So old grocery stores will do a very simple policy called first come, first serve, or we call it first in, first out, that just says when you get in line, that's the order that you go. So this is what the early computers like the UNIVAC did. When you walked into the computer room, you got in a line, and when your program was next to run, you got to run. The problem with this, as we all know, is when somebody shows up with a giant basket of food right in front of you, this is particularly a problem at Woodman's, what do you do here? So as we all know, grocery stores have figured out the solution to this, which is the express checkout lane, which basically says, we think that if somebody has a small amount of things, they should get to go first. They should get to go earlier if you have just a few items than if you have a lot of items. And in fact, this is exactly what operating systems do. When the operating system looks at these two things, it will look and say, does one of these need only a little bit of time and one needs a long amount of time? And if one needs only a little bit of time, like the word processor needs maybe a second to draw a character on the screen, it will say, I will stop running whatever I'm doing and run this word processor and let it finish, and then I'll resume the long-running task. Because the fact is, if this finishes in 1 hour and 1 second instead of in 1 hour, no one will notice. So this is called shortest job first scheduling, and again, it's provably optimal to sort of get as many things to finish as possible, we can, as fast as possible. So where are things going now? Well, I have the obligatory machine learning AI agents here. So the obvious thing operating systems are doing at this point is they're always looking at bigger and bigger computers, faster and faster computers, of course. But what I think is more interesting is that, as I mentioned, operating systems have to make a bunch of decisions. They have to decide which program to run. They have to decide which data to keep in memory, which data to remove from memory. They have to decide how to prioritize between all the different things they could do at once. And this is a place where they're using very, very simple ideas like shortest job first, least recently used. But there's a lot of promise of saying, can we learn more? If the operating system has seen your program execute for the last 15 minutes, maybe it knows a little bit more about what's about to happen in the future. It can actually make a prediction of what's going to happen and use that to make these decisions. So this is where I think operating systems are going in the future. So thank you.
Thank you. Those were great talks. The quartet's going to come up, they're going to tune, and then we're going to start talking about music. And we can get rid of the screen, please. I've been trying to find a way to have the Pro Arte Quartet play at SoundWaves for 14 years, and we did it. Sally, can you just do a little show and tell with your instrument because it's so beautiful? Well, they can't see that. You have to. Yeah, but yours is amazing. It's the decoration on this viola is incredible.
It belonged to one of my teachers, so be kind to your teachers.
So, development in music, it means two different things. Probably means more than two, but I'm thinking of two, and I will get to that later. And we'll get to Schubert's music a little bit later. First, I want to say the kind of general development that composers use in writing a piece is something very similar to what we all do all the time. We say, hey, how you doing? Fine, right? Yeah. How's the family? Job going okay? Oh, I'm so sorry. Yeah, tell me what's happening. So, you know, we have a theme. The theme is how are you? What's happening in your life? And then we change our question a little bit and we get into a conversation, and that's development. And that's what composers do, because music is very abstract. So if it kept changing, we wouldn't be able to lodge anything in our memory. We wouldn't have a sense of a theme, and we wouldn't have a sense of the change in the theme. One reason why many people have trouble with a lot of the atonal music in the 20th century is that they have trouble remembering what happened, because our brains aren't organized to hear atonal music, I guess, apparently, to the extent that they are organized to hear tonal music. So a composer relies on us to remember a theme, and largely through repetition of that theme. So repetition is a very important part of music, but also through development of the theme. So there can be a musical gesture which comes back. And one of the greatest examples of this is Beethoven's Fifth Symphony. Ba-ba-ba-bum. And that thing, that one little four-note motif, pushes the action for the entire movement. So it's not that surprising that that movement of orchestral music is probably the most famous movement of orchestral music of all time. It sticks in our head. We can remember it. We can follow the argument that Beethoven is laying out for us. So what we want to do when we listen to a piece of music is we want to see what are the themes being given, how are they structured, and then where do they go? So that's basically the more general kind of musical development. And note that one thing that a composer can do is give you a theme and then do something completely different. And we go, oh, something different. We remember the first thing, now here's a new thing. So the conversation can change the subject. Or if you want to think of it like a movie, the scene can change, or a theater production. This is now scene 3, and it's set in the village house. It's no longer set in the city apartment. And composers can do that just by changing the material. But if it changes too much, you're not going to recognize the interrelationships between the part of the piece. You're going to feel that it's disorganized and potentially not have a reaction where you're following the storyline. We see this in books. If anybody read any of the Game of Thrones series of books, there are so many characters in these books that you're reading along, and then all of a sudden you see some name, and it's like, I think I remember that name from 5 books ago, but I have no idea who this is. And in music, because it's so abstract and because it unrolls in time, we can't really go back. I guess now with recordings we can, but the unfurling of music in time means that the thematic material needs to be obvious enough for us to hang on to it, right? Okay, so that's one meaning of musical development. It also has a very specific meaning in music of the classical period and into the Romantic period and to an extent into the modern period. So their composers became interested in creating larger structures than just a song. So a song can have, you know, a verse, can have a refrain, it can have a chorus, a fairly simple structure. But if you want to write a longer piece, you have to figure out how to organize that piece. And you have to do it in a human-centered way where we can retain in our memory again, we can retain what we've heard before. And so we see the emergence during the classical period. And by classical, I don't mean classical music like what you hear at the Overture Center. I mean the classical period. So think Mozart, Haydn, Beethoven. Sonata form was developed. And sonata form is a way of telling a musical story that can be much longer than song form and be coherent to the listener. And it's a 3-part form in which there's thematic material that's offered, and that is called the exposition. And then there's a section called the development section, and that is where that material undergoes transformation. So imagine, the first section, the hero. Here's the hero, and here's her family, kids, grandparents, blah, blah, blah. There's where they all live, blah, 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 blah. Okay, part 2, the hero's journey, right? And so now we see changing situations. We see the hero undergoing duress and thriving. And then part 3, the hero returns home, the recapitulation. And there's all kinds of rules that were developed to guide this composition, the result of which is you can have a 12-minute movement like you will hear in a few minutes and follow the storyline even if you've never heard it. And it is organized and satisfying. So what I want to do with Pro Arte Quartet is go over some examples because I want to have you kind of load into your memory as a prelude some of this thematic material and see how Schubert, who's a classical period composer, and by the way, this piece is 201 years old. We should have done it last year when we did anniversaries all year, but that's okay. 201's a good anniversary too. So I have some musical examples that I want the quartet to play. And so the opening material is really monumental sounding. And could you please just play the first 4 bars? So a long note followed by ba-ba-ba-bum. And that ba-ba-ba, that's 3 notes in one beat. That's called a triplet. And that's going to become very important. That's going to be like a signpost, like a symbol that keeps recurring in a book. Okay, so we're going to be listening for that triplet thing. Also, notice it's interesting. The piece starts with a unison, and then it spreads out from the unison. Can you play it again? Everyone will hear that. Everyone's playing the same first note, and then they all separate from each other. Thank you. Okay, now Schubert develops this theme of the triplet, ba-ba-ba-bum. And I would ask you to play from the beginning up to the fermata, and everyone can hear where this triplet theme starts developing and repeating and changing. Thank you. I just want to point, can I be a little bit of a music theory nerd here for just a second? If you could play from the pickup from ba-da-da, where it gets after the first 4 bars, and this starts with the triplet, ba-da-da, okay, but then just a second later, there's 3 notes, but they're not a triplet, they're much slower, but the notion of the 3-ness of the triplet is heard slower. Can you just play from there, from that spot to the fermata again? Again, 1, 2, 3. So we have, even though this kind of music is very different from the thunderous beginning, we still have that triplet just much slower. Okay. Now, could you please play the second theme? So in sonata form, we have a first theme, and then we have a second theme, and then they sort of dance together in the development section. So I want you to hear the second theme. So could you play just the violins from 61 to 66? Thank you. Very, very different material, right? Not triplety, very different feeling in that material. It contrasts. So I was saying a change of subject can be an aspect of development, and that's built into sonata form, where the second theme is always very different from the first theme. Could we add the cello to that passage, but still no viola? Good. Now, can we add the viola? Because there is a little underpinning of this that you may recognize. So it's kind of buried in the texture, but the viola is playing triplets. So we've moved away, but we still have the triplet happening underneath all of that. Okay, now let's go to the development section itself. And in development sections, as I mentioned, all kinds of stuff happens, and composers love changing keys and having surprises. But one thing that's cool about this development section is it has an announcement in the second violin. So Suzanne, could you just play this little announcement? And in this piece, that gesture is used to say, hey, check out this next thing that's going to happen. So now, could you guys play the development section up until the subito piano at 163? Great, thank you. So can you sense that the hero is in a strange land, and there's a changing landscape. It's almost like you can imagine in a movie where we're in a very exotic place, and little bits of material, melodic material, keep getting heard, and the harmonies are changing and changing, and we feel we're in unstable territory. Yes? Okay. So we're going to do one more little set of examples, and then we are going to hear the movement. So could we hear the cello triplets at 163? Good. Now could we hear the same thing with some violin? So now we're going to hear the triplets, which come from the first theme, and the material from the second theme put together. Thank you. And now let's hear everybody in that passage from 163 to the Subito Pianissimo. Thank you. So you can see that Schubert is building this structure which we can actually perceive. We latch onto these themes, we load them into memory because they're recognizable, and then when they start changing, we remember how they went the first time. A lot of listening to music has to do with memory, right? If something is not memorable, we can't detect the flow of it. But what's going to be, it's just an absolutely beautiful piece, and what's really incredible about it is that Schubert is able to build this very, very huge mansion out of basically almost everything in here comes from that triplet gesture and the ba-da-de-bum, ba-da, the second theme. So the Pro Arte Quartet will now play the first movement of Schubert's string quartet, subtitled Death and the Maiden, quartet number 14.